Okay, so let's wrap up this paper. Oops, I have to put it in display mode, only then I can bring up the laser pointer. So the title of this article is Unraveling the Complexity of Global Climate Dynamics, Interactions Among El Niño Southern Oscillation, Atlantic Meridional Overturning Circulation, and Tropical Basins across different timescales. Why am I reading it again? I hope I read it in the first podcast. But anyway, so there was another article early on, a few years ago, called Pan-Tropical Climate Interactions, led by Wenju Chai. The abstract there read, the El Niño Southern Oscillation, which originates in the Pacific, is the strongest and most well-known mode of tropical climate variability. Its reach is global, and it can force climate variations of the tropical Atlantic and Indian Oceans by perturbing the global atmospheric circulation, which is very common with the paper we are reading now. Less appreciated is how the tropical Atlantic and Indian Oceans affect the Pacific, which we read a little bit here as well. Especially noteworthy is the multi-decadal Atlantic warming that began in the late 1990s, because recent research suggests that it has influenced the Indo-Pacific climate and the character of ENSO cycle and the hiatus in global surface warming. So essentially quite a bit of overlap there as well. Discovery of these pan-tropical interactions provides a pathway forward for improving predictions of climate variability in the current climate and for refining projections of future climate under different anthropogenic forcing scenarios, which is also quite common with the other paper we are reading now. So is there anything wrong in that? Not really, but there are some overlapping topics anyways. Pan-tropical feedbacks affecting ENSO, as a summary of this paper, is like this. So you have the Pacific, which is the monster, so gets a big space here, let's say. I don't know what I'm looking for. So Eastern thermocline and SST can have a positive feedback or a negative feedback into the mean thermocline, which is essentially our Bjerknes feedback. And then you have wind anomalies in the Western Pacific, we mentioned a lot there as well, which can be start as a noise westerly wind bursts, which are synoptic weather events, but then they become so-called multiplicative noise, because then they become part of the signal by pushing the eastern edge of the warm pool towards the South American coast, and then the fetch and duration can increase and they can get stronger, and we saw some of that as well. Okay, so you can have from wind to the eastern thermocline a positive feedback, and then a positive feedback back to the SST, which is our Bjerknes feedback. Then that can feed on to wind as a positive feedback, which is part of the coupled Bjerknes feedback as well. If you don't know what Bjerknes feedback is, I will discuss it elsewhere. So this all is related to Pacific convection, which is typically located in the Western Pacific, and then it gets pushed to the east, as we already saw, either all the way to the East Pacific in EP El Niños, or get stuck around the dateline for the CP El Niños. And then you can have positive feedbacks onto wind and SST in the Indian Ocean, which can have a negative feedback back to the winds on the Pacific edge, because you have Western Pacific getting turned around by the Indian Ocean forcing, so the termination and the transition and so on. We can also have convection feedback to the Atlantic with wind and SST, which can have a negative feedback back to the Pacific winds as well. So you also have direct feedbacks between SSTs and winds over here in the Indian to Pacific. So there are all kinds of interactions that go on. The black loop represents the internal Pacific fast positive feedback in short arrows here, and delayed negative feedbacks with long arrows. Basin feedbacks include Pacific feedbacks onto the Atlantic and Indian Oceans in blue arrows here, that I already mentioned. Delayed negative feedbacks of the Atlantic and Indian Oceans onto the Pacific, so orange and green arrows here. Okay, and positive feedbacks of the Atlantic onto the Indian Ocean in yellow arrow I just mentioned here. Effects of atmospheric noise in the Pacific are indicated with the gray line here. Okay, so that's a very brief summary. It's a nice long paper as well. I wanted to mention it because this is a topic that continues to be debated, and reviews do come along because they add some details in terms of, let's say, AMOC's variability and trend in terms of internal variability and anthropogenic forcing, and then feedback of the AMOC onto the Indian and Atlantic Oceans, or El Niño, and so on and so forth. Okay, summary and discussion then. In this review, we assessed and summarized the current understanding of tropical variability and the interactions between the tropics and extratropics, including ENSO variability and diversity, the influence of ENSO on the tropical Atlantic and Indian Oceans, the influence of the tropical Atlantic and Indian Oceans onto ENSO, interactions of tropical basins at different time scales, AMOC variability and its relationship with the Atlantic multidecadal variability, the influence of the tropical oceans on the AMOC state and its variability, the influence of AMOC on ENSO and tropical variability, and the influence of other mid to high latitude processes on tropical variability. Obviously, this covered much more than the paper that I mentioned here. Okay, so usually when you want to propose and publish review articles, you have to convince the editor, unless the editor has invited you to do it, which also happens sometimes, especially if you have a long list of big names. Then you know that they have either sold the idea to the editor, or the editor has asked them to write one, and so on. Okay. Although ENSO is the most important mode of variability on interannual timescales, its characteristics are not stationary and may be influenced by several factors arising from different tropical basins and processes at higher latitudes. The strength and variations in these interactions among different tropical basins and latitudes can be modulated by changes in external forcing, either natural or anthropogenic, and may also be affected by nonlinear interactions among different modes of internal variability. Okay, so everything can wax and wane in strength, duration, in frequency, etc. Just by internal variability. You have weak ENSOs, strong ENSOs, multi-year El Niños, single-year El Niños, which are more common, multi-year La Niñas, and so on and so forth. Right? We discussed elsewhere also how El Niño tends to have multiple flavors, like Central Pacific El Niño, Eastern Pacific El Niño, Central Pacific El Niño, but La Niña tends to have one cluster. But now there are ideas that La Niña also has multiple flavors, and so on and so forth. Okay. In this review, we identified several knowledge gaps that require further attention from the community. How do AMOC-induced changes in Walker and Hadley cells affect tropical basin interactions at different time scales? ITCZ is not mentioned here, but typically AMOC-induced changes come through the ITCZ shift and hence project onto local Walker and Hadley cells. And they occur at different time scales. Are changes in Walker and Hadley cells induced by AMOC slowdown versus rising GHG levels similar? So is there low frequency variability in AMOC that's natural, or a low frequency trend, let's say in forced by anthropogenic forcing, that is also on also seen in Walker and Hadley cells? Are they similar or are they different? If this is true, do they enforce or cancel each other? So internal variability may be pushing in one way, and anthropogenic forcing may be pushing the AMOC in another way. So, or AMOC may be slowing down due to internal variability and greenhouse gas forcing, or Walker and Hadley cells may be directly responding to anthropogenic forcing as well. So all kinds of combinations are possible, of course. What causes the observed changes in tropical basin interactions on decadal or longer time scales? And often I worry about whether we misinterpret decadal, multi-decadal time scales as trends, and then we get obsessed with trends, because extreme events, heat waves, etc. But if there is a natural decadal time scale, let's say in the monsoon region, then the key question is, how is the natural time scale being modulated by greenhouse gas forcing and global warming, etc., right? Are they due to changes in the background climate associated with greenhouse gases and or other anthropogenic forcing, or natural external forcing? Are they simply related to the low frequency modes of variability, whether internally generated or externally forced? What are the possible two-way interactions between tropical basins and the tropics and extratropics at various temporal and spatial scales? That's a very broad question. Basically means we don't know much as of now, right? Finally, modern machine learning and artificial intelligence, MLAI, AIML approaches offer exciting new opportunities to study the interactions among tropical basins and the extratropics. If you don't know what AIML are, you can go look up podcasts on my channel. Basically, you can just give it all the data, and it can extract patterns and connections, links, correlations, and so on with time lags that help you then to go back to dynamic models or process understanding. So there are details like interpretable models and explainable models and so on. So AIML are basically physics agnostic. You give them data and that tells you what it sees in the data, and then there are interpretations needed to say what it's saying. So you still need domain expertise in terms of ocean atmosphere interactions, AMOC, etc., to understand what AI is saying. But AI can do a lot more than just simple EOF type approaches. Okay, deep neural networks and so on, deep learning can do a lot more. Okay, keep that in mind. Although neural network models have ENSO prediction skills comparable to those of dynamical systems, the advent of more advanced approaches such as convolutional neural networks, recurrent neural networks, and graph neural networks, and the rise of computers based on graphical processing units, GPUs, is a game changer. So AI can help with data analysis, of course, help improve the models and model interpretations, and make predictions as well, and they can be much faster than dynamic models, which can also help make multiple realizations and so on. So lots of topics in this direction that I have discussed in a number of podcasts on my channel under Introduction to Climate Science, where this will also go, but that's a different playlist on AI and climate in AI and ML in climate modeling, predictions, etc. Okay, in climate research, there we touch a little bit on what CNN, RNN, and GNN are as well. Okay, in climate research, the most exciting result is the demonstration that GNN-based approaches outperform world-leading numerical weather forecasts at a fraction of the computational cost. I've discussed that paper there. In addition, CNN-based approaches have delivered remarkable seasonal prediction gains, extending ENSO predictions from 12 to approximately 18 months, and achieving the first skillful predictions of Atlantic Niño events months in advance. Okay, ENSO prediction skills can be extended by including interactions with other tropical basins and the extratropics. So we are up to reference 396 here, so you can see how many references there are. By performing better than CNN and RNN techniques, the transformer approaches have delivered three-dimensional models that predict ENSO events 18 months in advance and offer new opportunities to study tropical dynamics. The trick with ENSO prediction also is that ENSO happens in the deep, tropical Pacific and has global teleconnections. In the tropical Pacific itself, it affects fisheries, for primary production, rainfall distribution, etc. But we care most about it because of what it does on land. Dust storms in Australia, wildfires in Indonesia, droughts over India and heat waves elsewhere and winter storms over US and so on and so forth. So even if you predicted ENSO, you will need another step where you should be able to predict the teleconnections, because the teleconnections themselves are changing with climate change as well. So El Nino itself changes, its teleconnections change, and so it's a complicated business. So ML, AI and ML are taking us in that direction in any case, but it's a long way to go still. The number of papers that come out on AI ML are growing also, so that means we are making much more rapid progress, as well as there are incremental changes made with AIML. Despite these advances, developing AIML models to study climate remains a challenge because of the limited data available for training low frequency and long-term evolving changes. So you probably have an intuitive sense that AIML is basically being trained on data, and then it's doing something with that training for a situation it hasn't seen, like predictions. But if you want decadal interdecadal interactions between AMOC and interbasin and back to exotropics and so on, then you need data that's that long. Typically reanalysis products are used, and AIML may be stumped if it is if there are emergent solutions in the system that AIML hasn't seen in the data, so it may or may not be able to capture regime shifts and other events that are not there in the data that's used for training. So many details there. Transfer learning and hybrid approaches are being developed to overcome such issues. Thus, AIML approaches may allow for a deeper understanding of the issues discussed in this review. So transfer learning is basically it's trained in one situation, but it can transfer that knowledge to another situation where there is data, there is a lack of data, and so on. Hybrid approaches is where you are using some physics-based data-driven model, data-driven physics model combining with dynamic model, that is numerical computer model of the primitive equations or driving equations. So this hybrid approach. So AI can help improve parameters like mixing, or can directly couple to speed up some part of the model by directly relying on data-driven physics. Okay, so I'm just being kind of brief there, but I have a lot of podcasts on these topics that you can look up. Okay, so that concludes this nice long paper, which I have reduced to relatively brief summary. Even then, this is almost 80 minutes long, so you can imagine reading the paper will be quite much longer as well. So hopefully this summary helps you in case you wanted to skip reading the whole details, or your technical expertise is stumping you in terms of reading the paper. Okay, anyway, see you in the next topic.